All right, here is the first of what I'm sure will be many more. Limit definition of the derivative examples. Let me make that way smaller. Okay, so say we have f of x is equal to 2x cubed, and we want to find the derivative, which is a function that will tell us the slope at any point. So in order to find slope, first we're going to think about finding the slope of a secant line. So a secant line is a line, and since it's a line, it's only going to have, we're only going to worry about 2 points on it, even if it did cross at 3 points. So we're going to pick 2 points, and we're going to, that are on the graph, and we're going to draw a line between them, and we're going to find the slope of that line. So the first point will just be a point where we plug in x. So this is our x1, and we get out this for y. So we're working very generally. Our second point, we're going to add a little bit to x. So we're going to add h. So we're going to find a point that's like a little bit. So if this was x, we're just going to find another point that's x plus h. And h could be negative, so we really could be going in any direction. And then we'll replace x with x plus h. And that will give us another point here, x2, y2. This whole output here represents what would happen if we plugged in a new x value. So to find the slope, change in y over change in x, we do y2 minus y1 over x2 minus x1. And again, because we've worked very generally, we're going to have x's in our answer. And what it's going to give us is a way to find the slope at any x value. So it's going to give us a slope for any x on this line, this function, or on this curve, 2x cubed. So the formula y2 minus y1, y2 is 2x plus h cubed, y1 is 2x cubed, x2 is x plus h, and x1 is x. Okay, so as we can see here, let's just simplify. I'm just going to simplify the denominator for a second. So x plus h cubed minus 2x cubed. We can see in the denominator, x plus h minus x just leaves us with h. So now if we want to take our secant line and turn it into a tangent line, we would have to make h 0. If h were 0, however, the slope would be undefined. So since we can't actually make h 0, instead of actually getting the tangent line, we're going to take the limit as the secant line approaches the tangent line. So we'll take the limit as h approaches 0 of the slope here. So we're going to take the, and you can imagine from some of the animations we've seen, we're taking the 2 points that were on the secant line and we're having them get closer and closer together. And as we know with limits, we don't have to stress so much about what the actual value is. We can just see where it is headed. So once again, we know from our limits chapter, the first thing to do is try to plug in 0 for h. We can't do that. We would get it undefined. So what we want to try to do is see if we can algebraically manipulate this so that we can somehow maybe like simplify h over h, and then we'll be able to actually take the limit algebraically. If we were to graph this, there would either be an asymptote or a hole when h is 0. So we're trying to figure out what's going on there. So to do this algebraically, we're going to have to do a lot of algebraic manipulations here to the numerator. So I've said it before, I'll say it again, the hardest part of calc is the algebra. Remember that exponents come before multiplication, so you can't just distribute the 2. You have to take care of that cubed first. So I wrote out x plus h 3 times. Now, x plus h times x plus h is x squared plus 2xh plus h squared. You can draw yourself an area model or use the distributive property if you're not convinced about that. Next thing I will do is distribute an x, and then I will distribute an h. So again, this is just me doing a lot of algebra. So distributing the x to each term, and then distributing the h to each term. And again, I'm using the distributive property if you need to make an area model or draw some arrows. All right. And again, my goal here is I'm still trying to find the limit as h approaches 0, but I want to see if I can algebraically get rid of that h in the denominator. So now if I distribute the 2, 2x cubed plus 4x squared h plus 2xh squared. And if you need to pause at any moment to kind of convince yourselves how I did this, that's always acceptable. All right. So now we have everything in the numerator in standard form. So now we can look and see here, 2x cubed minus 2x cubed is 0. So those two are going to add up to 0, so they will be gone. Now you can see all of the remaining terms have at least one factor of h. So I can use the distributive property and factor out an h. I can take an h away from each term and kind of undistribute it. So I can have h. So now I'll be left with 4x squared here because the h has been factored out. And then I'll have 2x times h. And then here I'll be left with 2x squared because the h has been factored out. This will be 4x times h and 2h squared. So I took away an h from each of those terms. It's factored out front here. And I have an h in the denominator. So now, similarly to what we saw in the last unit, we can see h divided by h is going to make 1. So now when I take the limit, I'm only working on the limit as h approaches 0 of just this guy here, 4x squared plus 2xh plus 2x squared plus 4xh plus 2h squared. And now I can plug in h without anything, I can plug in 0 for h without anything going too crazy. So I'll be left with 4x squared. When I plug 0 in this term, it will become 0. I don't have to add it. 2x squared. When I plug 0 into this term, it'll become 0. I don't have to add it. Same thing here. So the limit as h approaches 0 is 4x squared plus 2x squared. It's 6x squared. So what is that telling us? So that is called the derivative. I'll write a little bit over here for a moment. Sorry. So if this is my function, f of x equals 2x cubed, this function called the derivative, which is sometimes written as f prime of x. Another way to think about it, there's two different notations, dy dx. And I like this notation a lot because it takes you back to the idea of the slope. So instead of the slope of the secant line, which is between 2 points, it's the slope of the tangent line. So change in y over change in x, where there is no difference between the 2 points. So this is a function which will give us the slope at any point on the original function. So say we want to know, so again, remember we said there's two ways you can think about it on this curve, 2x cubed. If you want to be at this point right here, you can think it's the instantaneous velocity, or it's the slope of the line tangent to the graph at that one point when x is 1. So when x is 1, if you plug it into this function here, f prime of 1, you'll get 6 times 1 squared, which is 6. So that means on this function, f of x equals 2x cubed, when x is 1, the slope is 6. So the slope of the line here that's tangent to this graph, all right, the slope here is 6. The instantaneous velocity, the change in y over change in x exactly at that point 1 on the graph of 2x cubed is 6. And we got that from using our slope function right here, or in other words, our derivative.